the potential of a given channel L. So in a given channel L, we can solve this equation that defines the delta PS of L, putting V effective equals 0 because it is what we want to determine, V effective. So we solve just this equation. And so if we have a recipe to determine the pseudo wave function, this potential of this L is taken as the local potential. So one reason why the local potential is important is that, as we will see later, this is the only potential that remain for all the L that we do not pseudize. So we will determine pseudo potential for a maximum angular momentum L. For all the other L, so all the L larger than this maximum L, the only potential that acts is this V effective. So it is not invariant. The procedure is not invariant with respect to what we do in V effective. Okay, and so what remains to discuss is how do we determine the pseudo wave function C. Okay. So there are two recipes that are available in LB1.x. I started describing this method of Kerker that is not implemented, but it was the starting point for the method of Trulli-Martins that is implemented. So in this method, what one does is that it takes as phi L simply the exponential of a polynomial and multiply by this r to the L plus 1 that gives the correct behavior close to the origin. So a very simple, the simplest function that is always positive because it is the exponential of a polynomial that you can think of. And this polynomial is taken like this without the linear term that would create some cusp that is not so already from Kerker it was recognized that to have this cusp in the potential was not, in the wave function, the cusp at the origin would not be positive. And so there are 4 parameters, and with 4 parameters we can impose 4 conditions. These 4 conditions are the continuity and the first 2 derivatives. So this fix 3 parameters, and then the norm-conserving condition fix the 4th parameter. These 4 parameters determine the potential. The only defect of this Kerker potential is that it is not optimized with respect to the number of plane waves that are then needed to describe the wave functions in the solid expanding plane wave. And so the Trulli-Martins method that generalizes this Kerker recipe is more useful and is always used instead of, so in our code at least we don't have Kerker, we have Trulli-Martins. Trulli-Martins choose simply an higher order polynomial up to 12 order and throw away all the odd exponents, and so you remain with 4 more 3 7 parameters. So the 4 parameters as Kerker give the same condition as Kerker, and so other 3 parameters allow to impose 3 additional conditions, and these 3 additional conditions are other 2 derivatives at the matching point. So in the Trulli-Martins method, also the 3rd and the 4th derivative of the pseudo wave function is continuous. And then a condition that Trulli-Martins found is very important for having a small number of plane waves in the solid is that the potential, the resulting potential, the effective plus the delta VPS, has 0 curvature in the origin. And so, imposing this additional 3 constraints that generated pseudopotential that are very, very good with respect to the to the number of plane waves that are needed to describe them. And therefore, this is implemented.
What condition allows you to throw all the order? What kind of symmetry?
All the order.
Why it is thrown?
No, it is their choice. I mean, the first the R coefficient is usually thrown away because otherwise there would be a cusp at the origin. And also they find that also the other odd is. I mean, it's better to throw away the other odd. The other recipe that we have implemented, that is alternative to these three-lemma things, is this method of Rape, Caxiras, and Joannopoulos, this so-called RRKJ method. However, what is implemented is only a one of the many forms that they suggest. In particular, we choose to implement only the case in which there are just three Bessel functions. So in this approach, the pseudo wave function before the core radius is given by spherical waves, by spherical Bessel functions, and you have 6 parameters, alpha I and qi. The qi are determined in such a way that all these Bessel functions have the same logarithmic derivative at the matching point of the all-electron wave function. And then you remain with 3 parameters that can be used to impose the same condition as Kercher. So continuity of the function and of 2 derivatives and the norm conserving condition. So actually this, it was found in other in some paper that this is a very convenient choice just to use these 3 Bessel function, and to use more Bessel function leads to more freedom, but usually to pseudopotential are more difficult to determine because they are not totally determined by the conditions. So you need to impose a constraint on the kinetic energy that we avoided. Maybe some other codes can exploit this property, but we have not implemented. I mean, they are not implemented in this LD1 code. These pseudopotential are quite good. So when it is possible to construct this Rape, Caxiras, and Joannopoulos recipe, it works quite well. The problem is that sometimes, so there is no guarantee that this wave function is positively defined. It could have a node. And therefore, when there is a node, you cannot use the pseudo wave function. And so the usual way is to change, so that we use at least, is to change the core radius in such a way to avoid the nodes. But sometimes this restricts a little bit the values of the core radius that are available with this method. And so sometimes one has to use the Trulli-Martins method. Okay, so let's now discuss. These are the 2 things that we have to impose to generate the pseudopotential. And so it is these core radii that are the point of the pseudopotential. We have to give this core radii and which pseudization we use to say which pseudopotential the code will construct. Then let's see what we have to do to transfer this pseudopotential to the solid, or to another configuration, of the atom with a different occupations or a different charge density. Well, the first point is that from this effective potential we have to remove the Hartree and the exchange and correlation potential. Because if we change the valence charge, we want to use this pseudopotential, we have to rescreen it with its valence charge. And so here we subtract from the effective potential the Hartree potential and the exchange correlation potential determined with the valence pseudo charge. It is clear that this screening, so if here we use just the valence pseudo charge, we are doing an error, especially in the exchange correlation potential, since this is not linear in the charge. And so to separate the charge in core and valence and to say that we can subtract only the exchange correlation potential of the valence introduce an error. An error that one can decrease or remove using for the exchange, just for the exchange and correlation potential, the total charge, the core plus valence charge in the calculation of the exchange. And then it is important that when we use this pseudopotential in the solid, we also rescreen it with the core and the valence charge. This approximation is known as nonlinear core correction, and it is quite important, especially in magnetic system, in magnetic configuration. So if we want that the pseudopotential reproduce magnetic configuration. However, to describe with plane wave the complete core charge would be really impossible. And so what one does is that one pseudizes the core charge. For instance, in silicon, it is sufficient to have the correct core charge, for instance, in this region where there is an overlap with the valence charge. But what happens in this region is not necessary that is reproduced exactly, and so one can choose a core radius and pseudize the charge before this core radius. Actually, the code automatically detects the crossing between the valence charge and the core charge and take that as a core radius for the charge, for the nonlinear core correction, so for the pseudization.
Excuse me?
Yes.
In that figure,
Here.
is 0.25 atomic units the core radius?
Point?
No, what is the core radius?
No, the core radius would be about here. But it depends. I mean, this is just with the wave function. One should plot, and we will see how to plot the valence charge and the core charge, and see where they cross.
So that is where you would pick up the core radius?
More close to that. Automatically, the code take that point, the crossing point, as the core radius for the charge.
Okay, so here.
If you want to change that point, from here, it is approximately here, but it is not possible to see from this plot, because here you have the wave function. You will need the plot of the charge density. Okay, so this procedure of subtracting the Hartree and the exchange and correlation part is usually called the screening of the pseudopotential. So then we have to use this delta VPS determined for each L, for each orbital angular momentum in the solid. And so this is a function that becomes zero after the larger between the local radius and the core radius. And we have, in order to apply this potential, we have in the solid to take the pseudo wave function, the block function, for instance, and to project it on the orbital angular momentum L channel. And the projector can be written like this in terms of spherical harmonics. This is a projector that projects on an atom centered in the origin. If the atom is centered in some other point, you have to shift this spherical Bessel function to be centered close, to be centered on about the position of the atom. And so the form of the pseudopotential is the following. It becomes a function, so The fact to impose norm conservation means that we have to have a different pseudopotential for each orbital angular momentum. And this has as a consequence that we have to use projectors in the given orbital angular momentum in the solid, and so that the potential of the acted by the atoms becomes non-local, so it depends on R and R prime. And it has to apply by integrating over R prime multiplied by the wave function. So it has a local part here that is added on all the atomic position I, and a semi-local part. It is called semi-local because it is local in the modulus of R, and it is non-local in the angles of R and R prime. And these projectors project on the given orbital angular momentum L, and we apply this potential to the part of the wave function that projects on this channel. Okay? So, this is in general what happens. We obtain with this pseudopotential a non-local operator. Here written in semi-local form. So the transferability test, we have to now determine how good is this pseudopotential when we change the atomic configuration. So suppose that we have generated the pseudopotential, as in the case of silicon, on the neutral atom, the atom with occupation 3s and 3p, 3s2 and 3p2. What happens if we apply this pseudopotential to a configuration, for instance, 3s1 and 3p3? Or also if we want to reproduce the ground state 3s2 and 3p2, but keeping into account for the local spin density. So for the spin polarized, the fact that the silicon atom can be spin polarized. Does the pseudopotential reproduce the behavior in this configuration? It is clear that these configurations are more difficult than what we have done with the logarithmic derivative, because now here we have to subtract the R3 in the exchange and correlation potential calculated with the 3s2 and 3p2 states, and to add the charge density, so to redo another self-consistent calculation with the new charge density. So this is not guaranteed that the thing works. So the LD1.x allows to do these tests that we will see later how to do. You see on the fitting configuration, the 3s2, 3p2, there is basically, so it prints the all electron eigenvalue, the pseudo eigenvalue, and their difference. So from here we see what is the difference, how good is the pseudopotential, because it compares the eigenvalues, the pseudo and the all electron eigenvalue. On the configuration that has been used from the fit, there is no difference clearly. If we take this configuration, which an electron passes from the 3s2 to the 3p2, and it becomes 3s1, 3p3, we make an error of the order of 0.5 Rydberg. That is reasonably good. So what we require is usually to have errors of maximum a few millirydberg for configuration that differs of up to a few Rydberg from the original, from the one that has been used to generate the pseudopotential. Here it writes in the first configuration the total energy of the all-electron atom, the total energy of the pseudo-atom, and here instead the difference, so the energy of this configuration with respect to this, in the all-electron and in the pseudo case. So this difference that is written here, the difference between these two, gives an idea of how transferable is the pseudopotential, so with which precision it can reproduce this configuration. For a spin polarized configuration shown here, this is the S2 P2 equals one electron in the 3s up and one electron in the 3s down, and 2 electrons in the 3p up. So the energies that one obtain all electrons are these, with the pseudopotential are these, and this is the difference that is of the order of millirad. Note that this is the pseudopotential with the nonlinear core correction. As we will see, without the nonlinear core correction, this error would be larger. Okay, a last consideration on the fully separable pseudopotential. The semi-local pseudopotential have the defect that when you calculate the matrix elements between two plane waves, this is a matrix, so you have to calculate to keep in memory all this big matrix that is number of G vectors multiplied by number of G vectors. And so this becomes rapidly too large, so that these semi-local pseudopotential are not even any more implemented in PW. PW can only deal with this fully separable form. And what is the fully separable form? So suppose that we could write the pseudopotential in this form as a product of a function of R, or a certain number of function of R multiplied by the spherical harmonics, and a certain number of function of R prime. In this case, to apply this pseudopotential, we just need to have in memory all this vector k plus g multiplied by this product of beta and spherical harmonics. So the pseudopotential that we have has this form for the angular variable, but it is local in the radial variable. It is possible to find a way to write it into this form, and the answer is yes. That's been found by Kleiman and by Lander. Suppose that we define so we want a pseudopotential that has this form, so it is the product of two functions, one of R and one of R and this one of R prime, and that acts as the other pseudopotential that we have, the semi-local pseudopotential that we have. So in the atom we can do something like this. This appears as a rewriting of the thing, a simple trick, but it is very important. So if we define the projector beta as the product of the delta, the potential and the wave function, and the energy as 1 divided the integral of the delta V between two pseudo wave functions, okay, we can see that the pseudopotential, the non-local pseudopotential that now is a function of R and R prime, written like this, when it acts on the pseudo wave function, it has the same action of the original potential. And as a consequence, this an equation where we use this form of the non-local pseudopotential is equivalent, so as the pseudo wave function at a given L as a solution with the eigenvalue that corresponds to epsilon L. Because on this function, delta V and L, so it is simple to see that V and L gives this, because V and L applied to this means the beta applied to phi. The beta is this object, applied to phi means that we have to integrate this with another phi. And this gives exactly epsilon L. So it will give 1 divided epsilon L. That's simplified with epsilon L. You remain with beta L, that is this, delta BPS multiplied by phi L. The only problem is that this is an integral differential equation, and so even if there is this solution, by construction we have this solution phi L with no node, there is no guarantee that there is not another solution with one node but lowest energy. If the pseudopotential has this solution that are known as ghost states, it is not a good. It means that the semi-local pseudopotential cannot transfer into the Klein-Landau form. And these ghost states can be detected basically looking at the pseudo-logarithmic derivative, and if you end up with a pseudopotential that has ghost state, it is well probable that changing the effective potential and making it less deep, you can remove the ghost states. Okay, I think this concludes. So here you have a bibliography of what I've talking about, and now we use this concept in the laboratory to construct the pseudopotential. So I think we can do a break, and we convene, let's say, at 10, at 11:10 in the other laboratory.